Welcome to week 3 of the problem solving sessions for the course Introduction to Wireless and Cellular Communications offered by NPTEL. I'm your tutorial instructor Sachin from the EC department of the Indian Institute of Science. As usual, I'll be solving assignment questions, but since the supposed to solve the previous year assignment questions, but since the questions overlap with the current assignment, I will only give you the method to solve the problem and it is up to you to solve the actual problem. Question 1, you have the following figure. That's just an approximate figure. You can look at your own assignment. There should be a similar figure in the assignment. So this curve is distance versus received power in milliwatts. So the blue color is N1, light blue is N2, the pink color is N3, red is N4, this is N5. These are various path loss exponents. So for different path loss exponents, how does the received power vary with distance is given in the curve. Of course, curves are a bit different. You can look at your assignment question. Just drawn approximately. So which of the given curves corresponds to the highest path loss exponent among the considered cases? So you can go back and look at the lecture, and you'll see that there was a derivation for the signal to interference ratio, which was given. Okay, this week we were still dealing with the hexagonal cells, at least cellular communication. So everything is, and we are assuming that it's hexagonal. So C over I was 1 over I naught, which is the number of interferers, times d over r power eta. So what happens to C over I as eta increases? As eta increases, C over I increases. When d is greater than r, which is obviously the case. The cochannel cells are farther than the uh, your own base station. So that means the higher the path loss exponent, the faster your received power falls off. And that should enable you to answer the question. Basically, almost given you the answer, but still, just a little bit of work from your side is also required. Question number two, there are two statements, and we have to tell which of them is true and which of them is false. Which of the following statements is true? Statement 1 says low RSSI and high SNR is an unlikely scenario. Statement 2 says high RSSI and low SINR implies a bad channel scenario. Okay, which of these is a true statement? Is the question. Oh, let's consider RSSI and SNR. There are four possibilities for each of these. RSSI can be high or it can be low, and SNR can also be high or it can be low. That gives four possible combinations for your RSSI and SINR. RSSI is the a received signal strength indicator. So it measures the received power directly, and it can't really differentiate between noise and interference and signal power. It's just whatever you receive, including all the extra components. The SINR, of course, the RX qual is RX qual. Of course, you have to look at the frame error rate and bit error rate, and then you'll get RX qual. That tells you what is the effect of interferers. So your RSSI is actually used to tell whether you are near your own base station, near the base station in your own cell or far away. And RX qual will tell you whether there are interferers in your own channel or there are no interferers. If RSSI is high, that means you are close to your base transceiver station. If your RSSI is low, that means you're at the edge of the cell. Let me use a different color. Edge of cell. Next, when it comes to RX qual, if your RX qual is high, that means there is a lot of interference. Sorry, that means there is less interference. So, or no interference. So this and this mean low interference. If your RX quality is low, that means there are there is high interference. Looking at this, you can decide. Statement 1 says low RSSI and high SNR. So this is the condition given in statement 1. Statement 2 says high RSSI and low SNR. This is the condition given in statement 2. So in statement 1, you are at the edge of the cell, so you are receiving less power from your base station, and there is high interference. That is, a lot of interferers are present for using the same channel as you. Is that a highly and likely? Is that a likely scenario or is that a unlikely scenario? So statement 1, maybe I mixed up things a bit. Statement 1 means edge of cell, that is you are far away from your own base station, and low interference. So is it likely that you're at your edge at the edge of your cell, but there are no users in your core channels who are using the same frequency? And statement 2 says high RSSI and low SINR. So according to statement 2, you are close to your base station, close to your own base station, and low SINR, which means high interference. So is this a good channel or bad channel? It's good that you are near your base station and you're getting high RSSI, but is it good that there are more interferers, or is it bad that there are more interferers? So I've almost led you to the answer, just a little bit more, and you'll get the answer yourself. I can't directly tell you the answer because these are your current assignment questions. Next, we go to question 3. For a hexagonal geometry, which is a valid cluster size? We have 7, 12, both A and B, neither A nor B. This is actually something we studied last week. The cluster size N is the area of large hexagon by the area of small hexagon, which is equal to I square plus j square plus ij. Here you start from a cell, move I units in the horizontal direction and j units in in the 60-degree direction, or I should say in the direction 60 degrees to the horizontal. So this is not in the XY direction. You still have the X direction, but instead of going in the Y direction, you move along a line that is 60 degrees to the X direction, which will be from the center of your cell to the midpoint of one of your sides. So I and j must be I and j must be integers. Sorry, n must be an integer. So you check out what values I and j can take. Yeah, and I and j, I mean, all three must be integers. So you substitute different values of I and j and find out if you can express 7 or 12 as a number of this form for different values of I and j. So you can make a table 0, 1 or 1, 0, give a 1. That's trivial. We can have 1, 1, that will give you 3. So 3 cells per cluster. You can have 1, 2, which will give you, okay, 1, 2 you find out. Then you do 2, 2, 2, 3. You put in values and see whether you can get a 12 or a 7. That's how you answer question 3. Question 4 is, which of the following methods can be used to improve the carrier power to interference power ratio CORI in an interference limited system? First method is sectorization. Second method is intra-cell handover. Third method is frequency hopping. Option D says all of the above can be used. Let's see first sectorization. So here I have drawn a cell along with its co-channel cells. So these are not neighboring cells. These are co-channel cells. That means they are using the same frequency. Suppose I have my base station at the center. Of course, in real life scenarios, the base station cannot always be in the center of your cell. Ideally, at least we are taking it to be in the center just for analysis purposes. Now, what you do is suppose you have um, some frequency band is given to each of the cells. So all of the co-channel cells use the same frequency band. You split that into three separate bands, F1, F2, F3, and you say to serve users in this part of the hexagon, I will only use channels in the F1 band. To serve users in this part, I'll use F2 band, and in this part, I'll use F3. So you have, instead of an omnidirectional antenna, which is radiating at all directions, you can use directional antennas and you can transmit at different frequencies in different sectors. Now, what happens is when you are when you are looking at the interference, we'll consider downlink. So this is my mobile station. Now this guy is operating at the frequency F2. This sectorization pattern is followed by your co-channel base stations also. So everywhere it's the same. So in this sector he will use F1, here he will use F2, F3. Similarly F1, F2, F3. Now to this mobile station who is sitting here, he is receiving the transmissions from his own base station in the frequency band F2. Consider the transmission from base station 2, which is coming in this direction towards the mobile station. That transmission is actually happening in the frequency band F3. So there is no interference because F2 and F3 are orthogonal. The signal from base station 2 does not actually affect our mobile station because he is transmitting in this direction, in the direction of the mobile station. Here, he is transmitting with frequency F3. Similarly, here, base station 7, he is transmitting with frequency F1 in the direction of your mobile station, which again won't interfere with the transmission from your actual main base station 1. So again, transmission from base station 7 also won't interfere with the signal. And by the geometry of um, the co-channels here, your base station 6 and base station 3 also won't interfere because here base station 3 is using F3 and here base station 6 is using F1. So the only base stations in the or the only co-channels which are causing interference are base station 4 and base station 5 because in this direction it's using F2. Again, in this direction it's using F2, which is what your own base station is using. So now when you try to find uh, CORI originally without sectorization, CORI was 1 over I naught, which is 1 over 6 root 3 n power n. Now with sectoring, uh, in uh, this particular case, so this also depends if you're using it also depends on where your co-channels are located. Sometimes this and this can also interfere, but at least in this configuration, only base station 4 and base station 5 are interfering. CRI is there are only two interferers, so half. So it's only half of root 3n power n, which is three times your original CORI. Okay, so that is about sectorization. Next is intra-cell handover. So suppose again you have this one cell here and you have a co-channel cell here. Now there are this is co-channel cell. Here also we are considering co-channel cells. Suppose your user has been given some frequency F1, your mobile station, And here also there is a user who is transmitting and receiving at frequency f1. Since they're co-channels, they can it might turn out that both the users are using the same frequency. But what you can do is, if there are other frequencies available that are not being used by this second base station. So suppose there's a frequency f2 that's also within the channel that's not being used by any user in base station 2. Then you can hand over communication from frequency f1 to frequency f2. In fact, you can keep changing between frequencies within your mobile station can keep changing his frequency from f1 to f2 to f3, and he can do it randomly. In that way, you can decrease the chances that there is a interferer who is also using the same frequency, and that is called frequency hopping. So within the bandwidth available to each cell, a user can hop with, obviously the number of channels you can the channel width will be smaller than whatever bandwidth it's allocated to each cell. So there will be a number of channels in each cell, and a user can hop between different frequencies. And you can do this in a random fashion. So we've explained these things, whether they're useful to increase CORI or not, you have to think of that on your own. I've almost led you to the answer. Just a small last connection you have to do. Okay, we'll move on to question number 5. So all these you can uh, see in lecture 10 if you want a better explanation. The professor has explained in lecture 10, and question 2 we can watch lecture 11. There you can actually find the answer to the question. Question 5. Find the path loss exponent based on the following experimental data. assuming a single breakpoint path loss model. So D in meters, PR of D in dBm. This is 100 0. Next, I'll just write them as D1, D2, D3 and P1, P2, P3. So, what is the single breakpoint path loss model? In that model, what is the power received? Power received is the power transmitted. These are all in dBm minus 10 log to the base 10 of 4 pi d break or lambda whole square into d over d break power eta or n, sorry, n, which is the power received at d break minus 10 n log of d over d break. Oh, sorry, this is question 6, I think. Question 5 was question 5 was find the distance, find the difference between the measured received power and estimated estimated received power at 400 meters. Okay, so that is question 5. The data is the same for 5 and 6. Okay, now we have Um, the received power PR of D is PR of D break minus 10 n log of D over D break. That is all right. Now at you have to put in D is 400 meters. So the for the estimate, what we'll do is for the estimate assume D break is 100 meters, at which PR of D is 0 dBm, which is a reasonable estimate. And then substitute, okay, if you assume that is the D break, your PR of D will become 0 dBm minus 10n log of 400 by, sorry, D by 100. So it's minus 10n log of D by 100. This is your estimates. So we'll write a cap on it. PR hat, a PR cap, however you like to call it. That's the estimated power at distance D. Now you just have to substitute D is equal to 400 to find the estimated received power. Then difference between actual and, by actual I mean measured and estimated received power is PR of D minus PR hat of D, which is so D1 is 400 meters in the assignment question, so it will be P1 plus 10n log of D over 100. At this point, you just have to substitute the value of P1 and D and find, you'll get the answer. We'll go to question 6. Question 6 is for the same data for the data in Q5, estimate the path loss exponent using the least squares method. So here our aim is to figure out the exponent so that you have data points, your distance pair of d, you have data points like this. Then you have to fit a curve such that this error is minimized. The square of that error is minimized. So the objective function or the function that you want to minimize is summation of pi minus pi hat square. Again, we are assuming that the 100-meter distance where your P received is 0 dBm is the breakpoint. And for the remaining three measurements, we are trying to fit a line through it. So for I is equal to 1 to 3, pi minus pi hat whole square. D break is 100. So we already found pi hat of D. It was minus 10 n log of D over 100. So you do this for I is equal to 1 to 3, whatever values are given for D1, D2, D3 and P1, P2, P3. You'll find the estimates of the received power for those 3 points. Then you subtract that. Of course, the estimates are a linear function of n, your path loss exponent, which is what you want to actually figure out. Then you find j of n, that is the sum of square error between the measured power. This measured power is the power given in your table, P1, P2, P3, and the estimated power, which is pi hat of t, which you estimate for all three values, d1, d2, d3. Then we know that from calculus you should have studied that to minimize or maximize a function, the partial derivative of that should be 0. So you take the partial derivative of j of n with respect to n and set that to 0. Then you will get an equation which you have to solve for n, and whatever that value is, that will give you the path loss exponent, which minimizes the square error. So I've given you the formulas to do all this. Now you just have to go back and plug in the values. That much you should be able to do for the assignment. Question number 7. Consider a cellular system with hexagonal cells and a cluster size of 3. If a 120-degree sectorization is employed in a system, how many tier 1 interferers will be present in a worst case scenario. Now you have to draw hexagonal cells with 3 cells per cluster. Okay, maybe I should do the co-channels with the different colors. Another co-channel, another cluster adjacent to it will be this. One more will be like this. Another one may be like this. Maybe I should have done a different color for each of these. So there are 6 clusters which are adjacent to the main cluster in which our user is. And for cluster size 3, there will be, yeah, adjacent clusters can be done in this way. Of course, the orientation can be different. For example, you could have taken this thing as your cluster, but at the end of the day, you'll get the same answer. Okay, these are the clusters where you will find your tier 1 interferers. Now, suppose you consider, again, I'll assume that the base stations are in the center of the cell, and we'll do 120-degree sectorization. Before that, let's say my user is present in the edge of the cell, which is the he's present at the furthest point from your base station, which is the worst case. Then we do 120-degree sectorization. So that's the sectorization of your own cell, and you have to do a similar sectorization for all the other co-channel cells. Now, in this scenario, how many co-channels are in the same sector? So the sector for this base station, which is using, I'll draw only the sector which are using the same frequency. So the sector in the cluster number 2, which I just drew now, this sector, which is using the same frequency as this sector, it's facing away from our user. So this base station does not interfere. What about this one? Again, this sector is facing away from your user. So here's the user, but here's the mobile station. But the blue guy is transmitting at a different frequency in that sector. So he is using the same frequency in this direction. So that blue guy will also won't interfere. What about the red fellow? This guy's sector. I'm drawing the sector which is using the same frequency as the mobile station. I won't draw the other sectors. Again, this guy is also not facing your mobile station. So that guy also won't interfere. So these three to the right side of your mobile station won't interfere. But this sector, it is, so the user is in the corresponding sector for this core channel. So this guy will interfere. Similarly, the sector of the brown core channel is also in the direction of the mobile station. So that guy also interferes. And finally, Anyway, this guy will also interfere. His sector is also like this, which is in the mobile station is in the corresponding sector for that base station also. So there are three interferers. Well, now I already told you how many interferers there are. You just have to mark the right option. Okay, and now with question 8. In a normalized UV coordinate system, consider 2 points with the following coordinates. Point A is at 3 comma minus 3, and point B is at minus 3 comma 3. What is the actual distance between points A and B if the length of each side of the hexagon is 1.2 kilometers? This is from last week's lectures. Okay. Now the coordinate system is like this. So you have the center of one of your hexagons as the origin 0, 0, and you have normalized it. So this is the point 1, 0, and here this distance is 1, and let's see, the other axis is, sorry, I think I made a mistake in one of my previous answers. I said um, this axis is 60 degrees to the horizontal. It's actually 30 degrees to the horizontal, 60 degrees to the vertical. So in this question, your other axis, let me draw the hexagon first. Now that other axis will pass through the center of the adjacent hexagon. So this is your V axis, and this is your U axis, this is X axis. So yeah, again in the previous question, so you move I units in the direction 30 degrees to the horizontal, and J units in the vertical direction. So I had flipped the axis there, but I think the answer will end up being the same in that question. Not sure here. Okay, now in this type of setting, with these axes U and V, you have the distance between u1 comma v1 and u2 comma v2, given by d12, which is square root of u2 minus u1 whole squared. plus v2 minus v1 whole squared. So in xy axis, that's all there would be x2 minus x1 whole square plus y2 minus y1 whole square. But in the uv axis, you have an additional component u2 minus u1 times v2 minus v1 is normalized. So actual distance without the normalization. So to normalize all the distances, you would have divided all the distances by root 3r. Why we do that, you can see from the previous class lectures, previous week lectures. So the actual distance is root 3r times d12. Now you have been given u1 comma v1, which is 3 comma minus 3, and u2 comma v2, which is minus 3 comma 3. You just need to substitute the values and do the calculation. Calculation part, I think you can do. There's no need for me to do that. Question 9. If a signal to interference ratio of at least 10 dB is required for a satisfactory forward channel performance of a cellular system, what is the cluster size that should be used for maximum capacity if the path loss exponent n equals 3.8, assume 6 co-channel tier 1 interferers at the same distance from the mobile station. Okay, here we are assuming hexagonal tessellation since nothing is given, and we saw in one of the previous questions that C over I is equal to 1 over I0 root 3n over n. As C over I is the signal to interference ratio N is the cluster size, small n is the path loss exponent, and that's it. Um, so choose the cluster size to be the smallest possible integer value that satisfies CRI greater than or equal to the least required CRI 10 dB. Because as why the smallest value? Because as the cluster size increases, cluster size is the number of cells per cluster. So if there are more number of cells in the cluster, that means each cell can have smaller number of channels. So number of channels per cell is reduced, which means again from the trunking efficiency, the capacity is reduced. So the smaller n gives you the larger n reduces capacity and smaller n increases capacity. Since they've asked for maximum capacity, you should choose the smallest cluster size. But a smaller cluster size also gives you a smaller CORI. So the cluster size should be large enough to give you the desired signal to interference ratio of 10 dB, but it should also be as small as possible to make sure that you are operating it at maximum capacity. That is question 9. Question 10. Consider a cellular system consisting of 180 users in a particular area. Each user makes an average of one call per hour. On average, each call lasts for 4 minutes. What is the total offered traffic? Just give me a minute, I'll go to the washroom and come back. Okay, you are solving question 10. Solution is very simple. Total traffic is the number of users times the traffic per user. So this is the number of users. What one user, the traffic of one user is the average number of calls he makes in 1 hour times the average holding time, that is average call duration. In hours. This is in calls per hour. If you want the final answer to be in Erlang. So substitute the values and calculate the answer in Erlangs. Okay, next we go to question 11. What is the traffic intensity per channel? For a cellular system with 25 channels and a blocking probability of 5%. Use use an Erlang calculator, a table or chart or whatever you have. Search on the internet. I think at the beginning of assignment, an online Erlang calculator has been a link to an online Erlang calculator has been provided. So click on the link, go there, and find out what is the um, capacity. Use Erlang calculator to find capacity C for 25 channels and P of blocking is 0.05. So this is not C, this is A. Um, it's called traffic intensity. So there's a chart, uh, or there might be tables also which you can use, but I would suggest using the online calculator that has been given. That will give you the value of A. Then C is the number of channels. C is 25. So traffic intensity per channel is A over C. Question 12. We have 0.15 Erlangs of traffic per user. I won't write, since we are running out of time, I won't write the entire question. I'll just write the data. And users are uniformly distributed over the geographic area covered by the cells. How many users can be supported for 5% blocking probability? 5%, 0.05. For 25 number of trunk channels is 25 in a blocked call cleared system. What is the number of users that can be supported? And the solution is similar to the previous question where to use the Erlang calculator to find traffic intensity for given P and C, number of users is traffic intensity divided by traffic per user. Question number 13 is in the above question, if one channel is reserved for handoff, how many users can be supported? Solution is the same method. Now the number of channels is 24 instead of 25. And for 24 channels and blocking probability of 0.05, you have to find the capacity or the traffic, total traffic that can be handled. Then each user generates zero point 0.5 Erlang of traffic, 0.15 Erlangs of traffic. So the number of users is total traffic divided by traffic per user. So method is same as question number 12, and the key takeaway is how much does a does the loss of a single channel affect the number of users. You can do the same thing for different number of channels and calculate the number of users and kind of observe for each loss of one channel how many, what is the loss in the number of users that you can serve. Obviously, if you have lesser number of channels, then the number of users you can support will also decrease. By how much it decreases, you can calculate for different values and find out. Yeah, questions are same from your current assignment. Um, so no, it's okay. Um, you can see your assignment there. First question is, which of the given curves corresponds to the highest path loss exponent among the considered cases? And there was an explanation given in the lecture. Of course, the explanation was actually for CORI, but it will apply here also, where we are assuming, of course, this is assuming that the received power is interference limited. Then C over I is 1 over I0 into d by r power. This should actually be n instead of eta. N. So if d by d is greater than r, then as n increases, C over I increases. If d is less than r, as n increases, C over I will decrease. So first thing you have to find out is d greater than r. One way to think about it is n is the slope of, so alright. So in this case, n uh, of course d is the distance between co-channels that's greater than the radius of one single cell. So this is the distance between co-channel cells, which is greater than the radius of one single cell. So d over r is greater than 1, which means with increase in Pavlov's exponent, you will get increased signal to interference ratio. Then second question, which of the following statements is true? Low RSSI and high SNR is an unlikely scenario. Statement 2 is high RSSI and low SNR implies a bad channel. So high RSSI means that you are close to the base station. Low RSSI means you are at the edge of the cell. You are far away from the base station. And it is always good to be near your own base station. So high RSSI is a good thing. Then this SINR, which is the RX qual that tells you about the interference. If you have high SINR, that means there is lower interference. If there is low SINR, that means that there is high interference. And it's always good to have low interference compared to high interference. So from that you can uh, choose the correct statement. You can decide which is correct, which statement is correct. Both can also be correct. Statement 1 says low RSSI, high SNR, which means you are at the edge of the cell and there is low interference. So is that an likely scenario or unlikely scenario? When you are at the edge of the cell, you are um, of course we are um, when you're at the edge of the cell, you're closer to all your co-channel cells. So when you're closer to co-channel cells, is it more likely that you have high interference or low interference? That you have to think. And then for statement 2, high RSSI means you're close to your own base station. Low SNR means that there are a lot of interference. So even though you're close to the base station, since the interference is high, how will you classify that? Is it a good channel or is it a bad channel? That also you have to decide. Then for question number 3, they have asked for hexagonal geometry, which of these cluster sizes is valid? And we saw in in the previous week that the cluster size n is the area of the large hexagon divided by area of the small hexagon, which is I square plus j square plus ij, where in the normalized coordinate system, you move I units uh, in the direction which is 30 degrees to the horizontal and j units in the vertical direction. So uh, you're moving from one cell to um, a co-channel cell in this scenario. So I and j and n are all integers. So for different values of I and j, find out the value of n and see if it's possible to have I square plus j square plus ij be equal to 7 or 12, or is it possible to get both values by substituting different values for I and j and making a table like this. For 0 and 1, n will be 1. For 1, 0, again it's 1. For 1, 1, it's 3. So try out for different values and see if you get 7 or 12 as one of the possible values. Those are the first three questions. Okay. Now, uh, you're in question 14. Okay. Since we are running out of time, I won't write down the question. This is the same question as your question 14 in your current assignment, I think. So consider a seven-cell reuse cellular system in which an average call lasts 2 minutes. Seven-cell reuse is the hexagonal cell, the normal cellular system that we always study, uh, in which an average call lasts 2 minutes. So that is the holding time. It's 2 minutes. We usually want to have it in hours, so it's 2 by 60 hours. And the probability of blocking is 2%. The blocking is 2%, which is 0.02. Assume that every subscriber makes one call per hour. So lambda is one call per hour on average. Assume that block channels are cleared, so the blocking is described by the Erlang B distribution. If there are a total 168 traffic channels per cell, so K is 168 channels per cell, and a 60-degree sectoring is employed by removing the omnidirectional antennas in the system. 60-degree sectorization. What is the approximate reduction in the number of users per cell? So initially what you have is you have been given lambda and h. From that you can calculate the traffic intensity per user, which is lambda times h. You find out uh, if something in Erlang's. Then total number of users supported U will be the total traffic that can be handled divided by AU. So find A by using the online. Erlang calculator for now the number of channels per cell is for 168 channels per cell, and P blocking is 0.02. So find A from the Erlang calculator, then the number of users U is A over AU. That is the number of users if you don't do sectorization. Then for 60-degree sectorization, so when you do 60-degree sectorization in a hexagonal tessellation, one of these parts is 60 degrees. Sorry. Uh, yeah, one of these is 60 degrees. So the total angle is 360. So there are six sectors now. If you do 60-degree sectorization. So the number of channels per sector is 168 divided by 6, which is 28. So initially you could use all 168 channels in the cell, but now the channels have been divided and each sector is given only 28 channels. That means that each sector can only handle 28 calls at a time. Now, again, in this scenario also, P blocking, you want P blocking is something that the users are demanding, so it is fixed for good service. You need that much amount of P blocking. So in this problem, it is fixed at 0.02 P blocking. And then again, you use Erlang calculator to find uh, A, let's call it A dash, for 28 channels, and EB is 0.02. Now again the number of users U dash is A dash divided by AU, and once you have that, loss in number of users is U minus U dash, and this is in users per cell. Okay, question 15, 16, 17 and 20 are theoretical questions, so I won't solve them. Um, Question 18, if a random variable x follows a log normal distribution such that the random variable y is equal to log x. X is log normal, y is log x is normal, Mean 0 and variance 1. What is E of x? The mean of x. Now we know that y is log x. That means x is e power y. So the expected value of x is the expected value of e power y, which is minus infinity to infinity e power y, the density Fy of y of dy. And since y is normally distributed, um, its density is its density for normal distribution is 1 over square root of 2 pi into sigma. Sigma is 1 here, into e power minus of y minus mu. Mu is the mean. Mu is 0 here. So e power minus of y square over 2. This is the distribution of density of y. So put in y in the formula for in the integral, and then you have to solve the integral. Once you solve the integral, you'll get e of x is e power a for some a. So solve the integral to find e of x. So if a turns out to be, so I have eliminated the answer 0 for you. So you have to find out whether it is 1 e or square root of e. That you'll get by solving the integral. Then question 19 says a mobile phone receiver operates at 2 gigahertz in a bandwidth of 200 kilohertz at 300 Kelvin and has a noise figure 6 dB. The receiver is present on the um, cell edge and a minimum 4 dB SNR is required for reliable communication. Consider log normal shadowing effect with sigma is equal to 6 dB. Given there is a maximum power constraint of 1 milliwatts that a base station can transmit, find the maximum radius of the cell for 95% coverage probability. Assume the free space path loss model, and you are given that Q of 1.644 is 0.05. So temperature is 300 Kelvin and bandwidth is 200 kilohertz and noise figure is 6 dB. So the noise power is 10 log kTBF, which is 10 log to the base 10 of kTB plus the noise figure. 10 log F is the noise figure. So you substitute the values of T, which is 300, and B is 200,000, 200 kilohertz, so it's 200,000. And K, you can find it in one of the previous lecture, or you can just search online. K is the Boltzmann constant. Then you'll get the noise power. Next, you have the received signal sensitivity, which is equal to the SNR plus the noise power. So the SNR minimum required, you can look in the question, it's 4 dB. Then you have to add the noise power that you calculate here. Then you'll get some received signal sensitivity. Now you have received signal power PR is equal to transmitted power minus path loss minus the loss due to shadowing, which is X sigma. Transmitted power is, these are all in dB. So PT is 1 milliwatt. That's the maximum. So we take it in dBm. PT in dBm. Then you'll get P received also in dBm is 0. 10 log 1 is 0. Here is 0 minus the path loss is 10 log to the base n 4 pi d over lambda square. Lambda is C over F is 3 into 10 power 8 divided by, we're operating at 2 gigahertz. Then X sigma has been given to be 6 dB. Sorry, sigma has been given to be 6 dB. So we'll use that later. Now um, we have to rearrange the terms. Okay. What they're asking is maximum radius of the cell for 95% coverage. So P coverage is 95%, which means that P outage is, this is 0.95. 1 minus P coverage is the outage probability, which is 0.05. But P outage is equal to P, the probability that received signal power is less than receiver sensitivity. That is the probability that minus 20 log 4 pi d over lambda. So since it's log, I can bring the exponent down and write it as minus 20 log 4 pi d over lambda. Minus your X sigma is less than received sensitivity. You'll calculate, you would have calculated earlier, SNR plus PM. From that you'll get, if you rearrange the terms, probably that X of sigma is greater than the sensitivity minus 20 log the path loss. Now, since x sigma is uh, log normal distribution, you can go and check in the class. We normalize this by the value of sigma, which is 6 dB. You'll get the probability to be equal to Q of receiver sensitivity minus 20 log 4 pi d over lambda divided by sigma. So you can find a online calculator again to find the value of Q. And once you have uh, you find the Q value, that will be equal to the probability of outage. So actually, what we want is the distance. So we can't find the value of Q of this. What we want is P outage should be 0.05 because P coverage was 0.95. So 0.05 should be equal to Q of this inside quantity, but they have given that Q of 1.644 is equal to 0.05. So that means receiver sensitivity minus 20 log 4 pi d over lambda divided by sigma must be equal to 1.644. So log of 4 pi d over lambda must be 1.644 sigma minus it should be receiver sensitivity minus 1.644 sigma divided by 20. So d is lambda by 4 pi into 10 power receiver sensitivity minus 1.644 sigma divided by 20. The answer will be in meters if you write your lambda in meters. Okay, I've given you the formula. You just have to put in the values for PN, you have to find out. Then receiver sensitivity, you have to find out. And then lambda, you have to find out from the frequency and substitute in the final formula. Okay, that's it. The remaining questions are all theoretical questions, and you can answer them on your own from the by watching the lecture videos. All right, that's it for today's session. We will meet again next week.